Okay, so far we've seen, right, how we can do velocity versus time graphs. We've talked about how to find displacement off of those graphs. We've talked about derivatives, and then in the last section we looked at going the other direction. So we talked about finding the integration and whatnot. So we're going to kind of extend on that, build on that a little bit more here. Most of the integration and derivation stuff will still continue to be the same, but we're going to go more into acceleration, which will bring us back to the three big kinematics equations that we've had. Okay, so we'll see those pop back up in this section here. But anyway, let's get in with it. So going back to last year when we first defined average acceleration, right, the way that we define average acceleration is very similar to what we did for velocity. We said the average velocity was simply the change in displacement over time, right? So the average acceleration, right, and they do tend to use still that bar over it to represent the average acceleration. Okay, so that bar representing the average acceleration. But it's exactly how we defined it last year when we said that it was the change in velocity over change in time. Okay, so this was what we saw for a constant velocity, but constant velocities and average velocities we will assume are about the same if we're working with the average. And then we've talked a little bit about instantaneous acceleration as well, but we'll see it some more here. So we'll see several examples. This section is also going to be good for giving us some more complicated systems to work, because I know those are the toughest ones probably you're looking at in homework right now too. So how do we interpret? Let's just go back to the basics. How do we interpret the acceleration from a velocity versus time graph? Well, last unit, right, last section, we just saw that anytime I find the area underneath the curve, that would represent the displacement, right? So that would represent positive displacement. This would be negative displacement. We know that to do that mathematically, we do the integral. So if I've got a velocity versus time graph, the acceleration then is right going the other direction. So this goes back to what we did a little bit of last year anyway. But the acceleration is simply, because the acceleration is simply the change in velocity over change in time, well, if I just look at my variables on the x and the y-axis here, my y-axis is velocity, my time is t, so I'm taking the change in y over the change in x. And if I take the change in y over the change in x, right, then that's obviously just the slope of my graph. Okay, so if I want to find the acceleration off of a graph like this, I'm trying to find the slope. So once again, if I was doing this mathematically, that means I would be doing the derivative, right? So the acceleration for this type of graph is simply the slope. If I gave you the function for this, we would simply do the derivative, as you guys have already seen a few times now. Okay, so not too bad. Again, hopefully most of the review. This example here is very straightforward. The reason I threw it in is just to make sure we don't lose sight of what acceleration actually means. So a bicyclist has a velocity of 10 meters per second and a constant acceleration of 2 meters per second per second. Notice, yes, this is the same as meters per second squared, but the reason that I listed it out like 2 meters per second was so that we think about what acceleration actually means. Okay, so acceleration means every second it's telling us how much we changed the velocity by, right? So for this instance, again, hopefully this is pretty easy, but if we start with a velocity of 10 meters per second and we have an acceleration of 2 meters per second, then 1 second later we've changed by 2 meters per second. So 1 second later we would be moving 12 meters per second. 2 seconds later, well, for each of those seconds we've changed by 2 meters per second. So now we're moving 14 meters per second. Again, hopefully pretty straightforward, but don't lose sight of what acceleration actually means. Right? Acceleration is a change in velocity with respect to time. Part B, the bicyclist has a velocity this time of negative 10 meters per second. Again, at this point, pretty straightforward. The fact that it's negative 10 meters per second, but our acceleration is still positive, means that we're working against it, so it should be slowing down. So we would once again add 2, which would make this negative 8 meters per second, and then adding 2 more, make it negative 6 meters per second. So hopefully this example was pretty easy. I don't think you guys would have had any trouble, but like I said, I did want to emphasize the big thing here, the fact that the acceleration represents my change in velocity with respect to time. Next example, also hopefully not too bad, although this does give us another opportunity to look at the motion diagram. And again, I do want us to start working a little bit more with these and being a little bit more specific. I know last year I had you guys do some general motion diagrams, but we should really get in the habit of labeling everything that we can. So the motion diagram is really what I want to look at in this example. So it says basketball player starts at the left end of the court and moves with a velocity as shown in this chart. Let's just assume that the left end of the court means we're starting at a position of 0. Okay, so let's just assume that that's where we're starting. So if I draw my motion diagram again, I'm going to give myself just an x-axis here to work with. So I know then at 0 seconds, my basketball player here is starting at 0 meters. So for that 0th second, so at 0 seconds when it starts, it's the basketball player starting at 0 meters. What's his velocity at 0 seconds? Well, if I look over here at my velocity versus time graph, I can see that his velocity is also 0. So the way that I reflect that then in the motion diagram is I just don't put a vector, right? This dot doesn't have a vector on it because at that second, at that instant in time, it's not moving. Okay, so I don't have to worry about, doing any type of vector there. Obviously, I had a stray mark. And then you could space this out, so you could do every 3 seconds, you could do every second. You don't necessarily have to go all the way to 12, but I am going to do every second just to give us an idea again of what this should look like. Okay, so after 1 second, the two pieces of information that I want to make sure I know are where is the basketball player and how fast is he moving. Okay, so after 1 second has passed, I want us to know both where he is and how fast he's going. Well, to find out how fast he's going is pretty easy, right? If I'm looking at this, and really if I'm just looking at this point, right, it's over 3 up 3, so the slope is 1. So I know that at 1 second he's moving 1 meter per second. So that's hopefully not too tricky. But if I do want to find his displacement, if I want to figure out where he is, keep in mind I have to find the area underneath this. So I need to find the area of that triangle, which in this case finding the area of that triangle would actually just be 0.5 meters, since it's a triangle with a base of 1 and a height of 1 and then 1/2 of that. So if here's 1 meter on my motion diagram, I know my second dot representing 1 second, and it is good to label as much of this as you can. So the second dot representing 1 second, and then I know that at that instant time he has a velocity of 1 meter per second. Okay, so I just draw an arrow, not terribly long because it's not moving that fast, but an arrow going that way at 1 meter per second. So then after 2 seconds, how far has he gone? Well, again, I know that at 2 seconds he's moving 2 meters per second, so the velocity should be going about twice as fast. And then at 2 meters here, it'd be a triangle with a base of 2 and a height of 2, so half of 4. So after 2 seconds, the basketball player would be over here at 2 meters, right? So here's the second of his motion. Say that 3 times fast. And then at that point in time, his velocity is 2 meters per second, which again should be reflected. You should try to make this first one about half as big as the second one. We do want to try and keep it proportional. Okay, so you could keep going with this, right? You could keep going, so on and so forth. After 3 seconds, he would be a distance of about 4.5 meters. Again, if I found the area underneath that, so 3, 4, 5. So after 3 seconds, he'd be over here, and he'd be going 3 meters per second, so again, about 3 times as long as that first one. Okay, so you do want to be pretty clear in terms of, and I'll label that as 3 seconds, but in terms of all the motion, right? So make sure you're comfortable with that. Make sure you're also comfortable on a diagram like this, seeing at which point he turns around. So in this case, he turns around at 9, right? So however far this goes, eventually this would end, and then at 9 seconds over here, at some point, he would turn around. Okay, so you do want to list as much information as you can. For an example like this, it would be completely reasonable to, rather than doing every 1 second, to maybe doing every 3 seconds. Just make sure you label that in your diagram. Okay, so if you do choose to do every 3 seconds instead of 1, just make sure you reflect that with your motion diagram. And certainly try that on your own, and let me know if you have questions. But I won't take a whole lot more time to cover that here. So that first part there was maybe the trickier part. Hopefully the acceleration versus time graph we'd be pretty comfortable with, right? Because going back to what we just said, the acceleration is simply the change in velocity over time, or in other words, the acceleration is the slope. And so if the acceleration is the slope of the graph, in this case, when I make my acceleration versus time graph, it's just going to be 2 straight lines. Because I know that the slope is constantly a positive 1 here, right? So my m is positive 1 as I go up, and then here it looks like it's maybe, if I actually calculate that, I go from 6 down here to -6 in 6 seconds, so it's a slope of -2, right? So my acceleration versus time graph would again just be a constant. So for the first 6 seconds I would be at 1, and then all of a sudden at 6 seconds I would jump down to -2. Okay, so that's 6 seconds, and then down here at -2. Okay, so make sure you're pretty comfortable with that. My guess is hopefully you guys would have been comfortable with that already, but in case you needed a refresher, it doesn't hurt to see it. Okay, so the first two examples, hopefully not too bad. The big thing, and this is where we'll probably, so I'll do this slide as I finish this first part of the notes here. This is actually a pretty cool one if you want to see where the kinematics equations come from. Okay, so I'm going to show you where each of the three kinematics equations comes from. And you may very well, after this, feel a little bit bitter. You might feel a little bit cheated as of last year because I know we didn't really derive these last year, we just worked with them. But it is good to know. Okay, so the first kinematics equation, right, that we almost always fall back on if we can is VOTAP, right? The final velocity equals the initial velocity plus the acceleration times delta t. Let's start with where this one comes from. Well, this one's actually just the definition of acceleration, and I think I did show that to you maybe a couple times last year. But if we define acceleration as, so average acceleration, the constant acceleration, is the change in velocity over time. Well, can't we break up the change in velocity as my final velocity minus the initial velocity, and then obviously still over time? If I take this equation then, okay, so I've got v final minus v sub 0 over t, if I take that equation and simply solve for my v final, I'd multiply both sides by t, I'd add the v sub 0 over, and I would get v final equals v sub 0 plus at. Okay, so that first of our three equations, is really truly just a definition of acceleration. It's just the definition of our acceleration. Okay, so that one hopefully isn't too mind-blowing. The one that's pretty exciting here, and again, you may be a little frustrated that I didn't tell you this last year, but that's all right. But let's look at the second equation. So the second equation, which is delta x equals v sub 0 t plus 1/2 at squared, and we'll actually work with this a lot where we break up the delta x into both x final minus x initial. So we'll see this a lot more this year where we actually break that up into that. But this equation here actually has to do with two things. One, the first way that I want to show you this is just start with this equation and differentiate it, or I should say not differentiate it, integrate it. Okay, so take this equation right now and integrate that equation. So if I take this equation and I integrate it, what would happen? Well, if I integrate this, we can think of this as t to the 0th power, right? So if I integrate this, this would be v0 t to the first power. When I integrate this, this first power would become the second power, but then I would divide by 2, so it would be 1/2 at squared. And I know, based off of integration, that if I do the integration of my velocity, that is my position function. Look familiar? Look familiar, right? So this was something that I did mention with the seniors last year, which is pretty cool. So the integration of this actually then is where that equation comes from. The other way that you can get that, though, which is also pretty cool, is if you look at the graph. So if I look at the graph, right, we know that the displacement for a velocity versus time graph, right? So for a velocity versus time, the displacement equals the area underneath the curve, right? So let's look at the area. If here's my starting velocity, here's my final velocity. Notice the acceleration times t represents just the change from my starting to my final velocity, which makes sense, right? That's how we've defined this relationship. Okay, look at the areas. Well, if I find the area of this rectangle, if I find the area of that rectangle, that's my initial velocity, so my v sub 0, times my delta t. So this area here would be v sub 0 times delta t. The area of this triangle, right, the area of this triangle would be 1/2 the base, which is delta t, times the change in velocity, which is really just the acceleration times delta t, which when I clean it up is 1/2 a delta t squared. And then if I add those two areas together, I add v sub 0 t plus 1/2 at squared, and I find out that my displacement, which equals the area, is equal to that original velocity times delta t plus 1/2 at squared. So once again, we can see that the area, which is the same as integrating, it is the same process, but the area underneath this curve is where I get that second equation from. So this is pretty neat. I hope you guys think it's fairly neat and fairly helpful. You don't necessarily have to have these memorized, but it is cool to see where they come from. I'll pick up obviously then with part 2.